Hey everyone, thanks for attending this session where we'll be taking a deep dive into Istio auth policies. And so my name is Lawrence Gadban. I'm a field engineer at Solo.io, working on Christian's team actually. And so at Solo.io, we have a suite of products related to cloud native API management, application networking, and so on. And as part of our Glue Mesh product, we actually offer enterprise Istio support. And so that means that we've been working with organizations at various stages of their Istio journey. So there are folks that are, just exploring Istio, just, POCing and so on. We're also working with folks that have been running Istio in production. Kind of one of the common themes with most of them is that in some form or fashion, they are interested in using Istio security. And it makes sense because it's such a powerful feature with so many different pieces that it's a very desirable feature concept to use. But even still, there's still a bit of uncertainty in what actually is happening behind the scenes when you're using Istio security. So the goal today is to kind of take a deep dive into the various policies you configure, but even more importantly, we're going to look at how those policies are actually implemented down in the Envoy proxy layer. And so that will help just have a clear picture of what's actually happening. And then if things go wrong, you'll have an idea of where to look to troubleshoot. So let's go ahead and get started. To start off with, we're going to kind of take a look at the overall picture. So this is the security architecture diagram taken directly from the Istio documentation. There's quite a bit going on here. So from the control plane side, users or operators can create things like authentication policies, authorization policies, and those policies will get translated into Envoy config and streamed out to the various proxies that make up the mesh. On the data plane side, you can have east-west traffic from service A to service B. That will actually happen, the actual communication happens through the sidecar proxies themselves. Those sidecar proxies can communicate over mutual TLS automatically. When you have traffic that actually enters the mesh from, say, some sort of client or consumer, that goes through your Ingress gateway. And if it's leaving, that can go through your egress gateway. And at various, all of these places, you can do things like JWT enforcement, TLS, mutual TLS, and so on. So as far as the mutual TLS inside of the mesh, there's been a bunch of great discussion about this already. Just to recap, alongside with the proxies that run in the workloads, there's also an Istio agent that provisions the identity for those workloads. So, as the workload spins up, you're going to get a identity represented by a certificate and so on. Then that happens by the agent communicating with the certificate authority component of IstioD. And so you automatically will have an identity associated with those workloads. And so let's go ahead and kind of spend a little bit of time talking about the mutual TLS portion. So by default, Istio mutual TLS runs in permissive mode. And so that means that workloads will accept both plaintext and mutual TLS traffic. So if we look at this layout here, we have the foo namespace, and in that we have HTTP bin, the application, and a sleep pod. These both have sidecars injected into them. In other words, they're participating in the mesh, they have sidecars, etc. We also have a legacy namespace that has a sleep pod with no sidecar. So there's no sidecar injected. In other words, it can't make mutual TLS. It can't participate in mutual TLS with these workloads over here. So in this case, if we want to make a request from the sleep application over here to HTTP bin in foo, that would happen over plaintext. And since we're in permissive mode, that is allowed. But also in permissive mode, if you do have two workloads that are participating in the mesh, they do have sidecar proxies. Even in permissive mode, this traffic will occur over mutual TLS. So we have the sleep pod in foo that's making a request to HTTP bin. That communication will happen over mTLS, even though we are in permissive mode. And so let's kind of zoom in on this communication here. So this is kind of what it looks like. So we have the sleep pod is making a request to the HTTP bin service, port 8000 / headers. And so this HTTP bin service is kind of defined over here. This is the YAML for it. And what's important is that the service port is 8000, but the target port is 80. So in other words, the actual workload itself is expecting traffic at port 80. So you can see that here. And so this request from sleep is a plain text request. It's just HTTP. And there's the sidecar that lives alongside it that will actually essentially hijack that traffic. And it's expecting a connection at port 8000. And this is plain text. So then the request or the connection will be established with the sidecar proxy of HTTP bin. We'll get into the details of this 15,006 port here in a second. But this communication will happen over mutual TLS. And then eventually what will happen is the connection will make its way to the actual HTTP bin application at port 80, as we were discussing with the target port of port 80. And so, the actual communication between the applications and the sidecars is plain text. So it's transparent to the applications. It's really powerful. You don't have to make changes in order to get mutual TLS. So I wanted to kind of zoom in on each one of these legs, but in the sake of time, we're just going to focus on this one right here, the inbound connection of the server-side sidecar, essentially. So we'll go ahead and zoom in onto this Envoy, essentially. So we have an HTTP request being made to HTTP bin, and this is what that request looks like. We looked at the service definition earlier. Associated with that service is an endpoints definition, Kubernetes resource. And so this is what defines what endpoints are actually serving up that service, or backing the service. And so in this case, we have a single pod that is at this IP address 10.100.1.9, and the port is 80 because our destination port is 80. So the connection is actually being established to this IP and this port, right? And it's a Istio mutual TLS connection, basically. And so now we'll look at how Envoy actually handles this. So there's kind of two things going on here. One is that Envoy handles incoming connections with its listener component, right? And so on the left here, we have a listener config, and that's what this green box is representing, a listener at port 15,006. But our initial, our actual connection is trying to go to port 80. So this is where the IP tables kind of magic kicks in, and essentially it's hijacking that incoming connection and redirecting it essentially to this virtual inbound listener that's at port 15,006. And so again, there was a talk earlier that talked about this in a little bit more detail, but basically Envoy will be able to understand what the actual original destination was. In this case, it was port 80. So we talked about the listener, and the listener is what handles that incoming connection. So then we actually need to do something with it. And in Envoy, that's handled by filters, right? So there are network filters, there are HTTP filters later on when we're talking about HTTP. But we need to actually have our filters to actually do something with this connection. And so if you only had a single filter chain associated with your listener, that would be easy, right? Because you have a listener, you're listening on some port. As the connection gets established, then you hand it off to the filter chain and your processing happens. But in this case, we actually have more than one. And that's pretty common in Istio just because of the nature of how many depending on how many services you have in the mesh, et cetera, that you're usually going to have more than one filter chain that you need to consider for an inbound connection. And so when you have more than one filter chain, there is the concept of a filter chain match. And so this is essentially saying, okay, for this given listener, so in this case, for the inbound listener, we need to decide which filter chain to use. And so we need to evaluate some of the properties of the connection and determine which filter chain to actually use. So in this case, we have a filter chain match here in our listener config. And again, this config is sent by IstioD. Essentially, the control plane is sending this config to the sidecars based off the state of the mesh. And so we have a filter chain match here that is looking for a destination port of 80, which in our case makes sense because that's what we're trying to, connect to. The transport protocol is TLS because this is a TLS, even though it's mutual TLS, this is a TLS connection. And then this set of application protocols, this is necessary because this is essentially how, even though we're in permissive mode, the two sidecars can kind of determine that they're both speaking the same language as far as Istio mutual TLS. So because it's Istio mutual TLS, these application protocols are a match. And so we have a filter chain match based off of this connection. That means that we're going to select the filters associated with this chain. And that's how we're going to do our processing. But before we even get into the filters, there's another component essentially associated with this match, which is the transport socket. And so this transport socket is responsible for actually doing all of the TLS ceremonies or whatever you want to call it, right? So this is how we actually can do TLS at the transport layer. And so this is essentially zoomed in, right? So this transport socket has some config. This is kind of the zoomed in view. this is a little bit hard to read, but it's worth calling out that, so with that filter chain match that we had, we selected this transport socket. And then there's some config here that does things like, for example, this require client certificate's true. We're basically saying we're going to do mutual TLS. So, we're not just doing a single one-way TLS. As that connection is established, the server side is going to say, hey, I need to see your certificate to the client. And so we're enforcing that in the transport socket. We're also going to validate that cert with the root CA that's defined for the mesh. We're ensuring that it's a valid SPIFFE cert, and so on. And so the fact that this transport socket is associated with this filter chain match means that now we get to use this transport socket for this connection. So then we'll zoom back out, and the next step is really the filters, right? And so in this case, we're looking at network filter, the HTTP connection manager, or HCM, and that's really where all of the HTTP processing in Envoy happens. And so we have the HCM on this filter chain. And if we zoom in a little bit on the HCM, we have a set of HTTP filters associated with it. And so in this case, we have something like Istio authentication, Istio stats, and the router. So the router is what actually takes the request, the HTTP request, and routes it to whatever destination, the appropriate destination, essentially. And so if we're talking about an inbound request, this really is going to route to the application workload that's running inside of the same pod, right? And that's the last one in the chain because that's what actually does the routing. So that's kind of the theme, or that's kind of the pattern that we'll be looking at. So, the inbound listener gets defined by the control plane, and that's sent out to all of the proxies. And then based off the configuration that we have, based off the configuration that we as a user or an operator have made to Istio, these chains and these filter chains and so on are going to be modified to satisfy or enforce whatever kind of policies we define. So let's take a look at the first kind of policy we'll look at, which is the PeerAuthentication policy. And the PeerAuthentication resource is really about how mutual TLS is enforced. So basically, by default, we're in permissive mode, right? But you can change that by using a PeerAuthentication resource. And so you can scope this policy to various levels. So you can do things like a mesh-wide config, you can do a namespace-wide config, you can target individual workloads. And with PeerAuthentication, you can even go down to the port level. So you can have port level config for mutual TLS. And when you have more than one policy that matches, the most narrow scope takes place. So if you have like a mesh-wide config, and then you also have a specific workload config, that workload config will take place, will take precedence. So as far as the modes go, we talked about permissive by default, right? So you can accept mutual TLS and plain text. And so this explanation is taken directly from the docs. And in here is called out that it's useful for migrations. And really, unless you're completely starting from scratch, more often than not, you're not going to be able to have every single workload get a sidecar. And so you're going to have some legacy clients left around. And so that's kind of the value of permissive mode, where you can, iteratively start migrating clients to have a sidecar, to participate in mutual TLS. And so until you get every workload there, permissive mode allows that to happen. So strict mode is where you're only accepting mutual TLS. And that's obvious, that obviously is the most secure, because that means that all traffic to this workload is over mutual TLS. And so you have a well-known identity. You can this is only allowed if you have a valid certificate according to the mesh. And so this is kind of what you really want to get to if you're talking about mutual TLS. But it can be a journey to get there. So that's where permissive mode comes into play. It's worth calling out that you can also have this disable mode, which kind of shuts off mutual TLS. And so it's called out, you shouldn't use this mode unless you have your own security. One example of this is if you have applications that have their own certificate built into the image, for example, and it's kind of like a legacy solution, but you still want to run it in the mesh, you can at least disable mutual TLS for that specific workload. And then finally, for completeness, there is this unset, which essentially means inherit it. Inherit the mode from the parent if it has one. Otherwise, it's treated as permissive. I actually haven't seen this too much out in the wild. I'm sure there's a valid use case for it, but I haven't seen it yet. Okay, so we talked about scoping. So when you apply a PeerAuthentication, you can apply it as a mesh-wide policy, right? And so if you look at this example, what we're doing is we're creating a PeerAuthentication resource called default. We're creating in the Istio system namespace. This is kind of the root namespace by default. And then we're setting the mode to strict. And we don't have any selectors here. So essentially this is a mesh-wide config due to the fact that it has no selector and that it's in the Istio system namespace. And so when we apply this config, this peer authentication to the mesh, all workloads in the mesh are going to get, essentially they're going to get the effects of the strict mode. And we'll look at what that looks like here in a second. And then, as we mentioned, you can do namespace wide config. So in this case, no selector, but the namespace is foo. So in this case, we're applying strict mode to all of the workloads in the foo namespace. Then you can scope it down to target a specific workload itself. So in this case, we do have a selector in place, and we're selecting the, essentially we're selecting the HTTP bin application based off label selection. And so that means that now what we're doing is we're applying strict mode only to the HTTP bin workload in the foo namespace. And then the most granular is the port level scope. So what we're doing here is we're saying to the HTTP bin in foo, we want to disable mutual TLS on port 80. And so this, we kind of talked about it earlier. This is mainly useful if you have some sort of like legacy or pre-existing security solution that uses certificates, and you don't want Istio mutual TLS to interfere with that. It's also worth calling out that if you're going to use something like this, there is you'll likely need to use what's called a destination rule. So that's kind of a more general, Istio configuration that handles client-side config. Because most of the policies that we'll look at today apply to the workload. You're targeting a workload, and that's really the server side, if you will, right? So if you want to actually, interact with something, you want to change how the client's behaving with it, you can use what's called the destination rule. So for something like this, if you were disabling port 80 mutual TLS, you may want to say, okay, I'm going to create a destination rule that will, when I target port 80 on this workload, I want to use some existing set of certs that are not related to Istio mutual TLS, for example. So let's look at what actually happens when you apply strict mode. So first, let's look at permissive mode. And based on what we were talking about earlier, we have a set of filters and so on that are selected based off of our filter chain match. And so we have an mTLS match and a plain text match. So when Istio mTLS traffic gets to our inbound listener, we have a filter chain match that's looking for the port 80, the transport TLS, and then the various Istio protocols that we were discussing. And so this is a match based off that connection. So we're going to select our transport socket that we talked about and all of the filters associated with it. When we have a legacy traffic or plain text traffic coming in, we have a match for that because we have the destination port of 80 and the transport protocol of raw buffer. And so that raw buffer is essentially saying not TLS, right? Plain text. And so we have a match and we have a filter chain associated with it. So when legacy traffic makes its way to this listener, we'll select the filter chain associated with this match. And notice that there's no transport socket because we're not really defining anything special as far as TLS goes. So we'll use this one. So now when we actually apply strict mode, so let's say we apply the strict mode at the mesh level, right? And so every workload's going to get this change. So what ends up happening is now the plain text match, the plain text filter chain match, and the filter chain associated with plain text, they get removed entirely from the inbound listener. And so that means that now we're left with just the TLS match. And you'll notice that the application protocols that were defined here on the TLS match have also gone away because now we don't have to worry about kind of negotiating that we're talking Istio mutual TLS because in strict mode, everything is mutual TLS or Istio mutual TLS. So now that match is more straightforward. It's if the destination port is 80 and if the transport protocol is TLS. And so we're left with that single filter chain basically. So what actually happens when a legacy client or a plain text client tries to communicate with a workload that has strict mode enabled? So the request will come in and it's plain text. So the existing filter chain match that we were looking at, we have destination port of 80, which will match, but the protocol or the transport protocol is not TLS. So we don't have a match here. And from kind of the client perspective, they're issuing a curl request and then they see this command terminated. You're not seeing like an actual you don't see an HTTP response code or anything like that. You just see it fail. And so if you look at these are the debug logs here of the actual Envoy proxy. And what's happening is, you'll see that the connection was accepted, but then the connection handler is saying, I'm closing the connection because there's no matching filter chain found. And so essentially by turning on strict mode, we as the sidecar proxy will not even accept the connection. So we're kind of just, shutting down even any kind of incoming connections if they're not Istio mutual TLS. So, and then now when we have a mutual TLS request connection come in, we have our match because its destination port is 80 and the transport protocol is TLS. And so we use the filter chain and the transport socket associated with that match, which includes our transport socket that knows about the mutual TLS. We were going to validate with our root CA, et cetera. And then we have the filter chain that's associated with it. So we're good to go there. So now we'll look at there's another change that's made when we're in strict mode. So this Istio authentication filter is an HTTP filter that was in the chain. It was in both of them that we were looking at earlier. And so when we were in permissive mode, this is kind of a sample of what the config for that filter looked like on the down at the HTTP filter level. So in that case, we had mTLS mode permissive, and then when we applied our strict mode, now we have mTLS with no permissive mode. So essentially, we're running in strict mode. And so when we're running in this mode, this Istio authentication filter, it will validate that the connection was using mTLS and that the peer certificate was a valid SPIFFE cert. And then what it will do is it will save off this peer authentication data for use in later filters. And we'll look at this in more detail here in a second. Just for completeness, I'll call out that it does not validate the trust domain. So you can see that this is kind of part of the config, right? So skip the validate of the trust domain is set to true. This is mainly used when you're using multi-cluster, kind of outside of the scope of what we're talking about today. But I will call out that if you do want to do some sort of validation of the trust domain, one of the options you have is by using authorization policies directly to do that. Okay, so again, we're looking at some debug logs. This is this is the sidecar proxy for HTTP bin. Remember, the request was coming from the sleep pod, and this is the Istio authentication filters debug logs. So you can even see here, right? So the mode is strict, SSL true, etc. What we're doing here, you'll see this set peer from X509 as this cluster.local namespace foo, SA service account sleep. This is essentially the SPIFFE or the workload identity of the source. And so we're setting the principal from that. And then you'll also see that we're saving some dynamic metadata. And of note, you'll see that in that dynamic metadata, we're setting the key of source.namespace to be the value of foo, which is the namespace of the request of the initiator. And then the principal, the source.principal is set to that identity that we were talking about. And so what ends up happening is the Istio authentication filter uses another Envoy component called dynamic metadata, which allows filters to essentially communicate with each other. It's going to save that data for use later in, for example, authorization policies. And so we're setting a source.principal. So in our dynamic metadata for Istio authentication, we're setting source.principal to be that identity, and we're setting source.namespace to be foo. And that's how we're going to be able to access it later on. So that's kind of it for the peer authentication piece. Let's take a look at request authentication. And so now we have a request authentication resource for that. So this is really all about authenticating the actual individual requests. And right now, the main way that you do that is with a JSON Web Token or a JWT. And so what you're specifying here is kind of where the token comes from. So by default, that's going to be the authorization header with the bearer prefix, the issuer of that JWT, and how to actually get the JSON Web Key Set or JOCs of that associated with that provider or that issuer. And so this is basically where the public key is, so that we can do verification on the JWT and make sure that it was signed by the correct private key, basically. And so Istio will take this and translate it to some Envoy config, and then we'll actually verify various pieces of the JWT itself. Again, similar to how the peer authentication worked, you can scope this to different, you can have different scopes for this. So you can do mesh wide, namespace wide, or workload wide. And you can have multiple of them, multiple of these. The end result of that is that they're aggregated, and what you're really doing when you do that is you're saying, I have more than one provider. So if I present a JWT if you have, say, 2 policies, one from foo and one from bar or whatever, if I present a JWT that's valid according to either one of them, the request is allowed, basically. And so again, here's a view of kind of the scoping, right? So in this case, again, in the Istio system namespace with no selector, that means it's mesh wide. So this request authentication config gets sent to all of the workloads, all of the proxies in the mesh. If we do a namespace wide, so no selector, but a non-root namespace, so namespace foo, all of the foo workloads will get it. And then, of course, you can target individual workloads. So in this case, we're targeting the HTTP bin app in the foo namespace. So it's worth calling out that you can do request authentication at the ingress layer, right? And normally, it's a pretty common thing to want to do this because request authentication usually corresponds to a client, like a human user or a client that's living outside of your mesh. And so it makes sense to do those at the edge, right? And so you can apply a request authentication config at the Ingress gateway, for example, right? So here's an example where we're applying a request authentication in the Istio system namespace that's targeting the Ingress gateway. And then we're defining our issuer and where to get that our JWTs data, our public key. And so in this case, now what we're defining is that the Ingress gateway is what's going to actually perform this request authentication. So, if we look at the kind of the data path, the data plane, the request path, users making a request with a JWT to the Ingress gateway, and now the authentication is going to be formed here at the edge. So if it doesn't have a valid request, it doesn't have a valid JWT, that request won't be authenticated even at the edge. And so it will be denied at the edge. But if it's allowed, then it can be forwarded to the upstream services within the mesh. It's worth calling out that if you do this, if you want to perform additional JWT-based logic, right, either whether that's writing authorization policies based on the JWT, or if your applications themselves rely on the JWT, so you have actual security features built into your application, you want to forward on that token. So as far as how that actually is enforced, we're adding another filter to the filter chain. We're adding the Envoy JWT filter. And so this JWT authentication filter is what performs the actual enforcement. So this will be added into the chain with associated listeners. And so in this case, this is kind of the translated config for it. Of note, you'll see this allow missing requirement. So the requirement on the JWT filter is a provider of what we've defined or allow missing. And so this means that if you don't present a JWT at all, the JWT filter will not deny it. It will allow it. So that's something to think about. So for example, if you have an invalid JWT, well, it's because the issuer doesn't match, the signature is not valid, it's expired, it doesn't have the correct audience. If that was configured, it will be denied. But if it is valid, or if it doesn't have a JWT at all, it will be allowed. And so then when we're doing request authentication, we also modify the Istio authentication filter to now perform origin authentication. And so there's actually not a whole lot of enforcement going on in the Istio authentication filter when we're doing origin or request authentication, but we are doing something useful as far as extracting the request principal. So let's take another look at the logs of the sidecar or the proxy that's handling the request authentication. So we're processing this JWT payload. You'll see that we're setting the principal based off of the origin. So there's the John. So we have foo globalcorp.io/John, and this is the origin principal that we will then save for later use. So this is the issuer and the subject, and so this is saved again in dynamic metadata, like we talked about before. So now that the Istio authentication filter can handle that, now the Istio authentication filter gets access to that data, it's going to store that in the dynamic metadata for use later on. And then of note, we're kind of storing the full claims of the JWT as well. So that's how you can do really complex or really fine-tuned rules based off of the JWT that you are validating or authenticating. And so quickly, let's run into the authorization policies themselves. So there's another resource that allows you to control, this is actually access control, right? And so In this case, you're defining a set of rules that say, for example, from or to. So based on the source of a request and the operations of the request, and additionally some optional conditions with the when field, you can allow or deny access. So what that means is that now you can allow or deny rules based off of any of the values that we were just talking about. So basically, what was the source of the request based on the peer authentication, or the source of the request based off the request authentication. And so authorization is kind of done in an implicit enablement fashion. This is what it's called out in the docs. So when there's nothing present, everything's allowed. But once you start adding rules, it will change the behavior. So if you have one or more allow requests, now you, or one or more allow policy, that means that now everything will be denied unless it was explicitly allowed. Deny policies are evaluated first, meaning if you have a deny rule, if you say you have a rule that matches and it's for an allow, if there's a similar rule that matches for deny in front of it, even regardless of the allow rule, it will be denied. And multiple policies will be aggregated, meaning that you basically don't have to define all of them in a single policy. You can have more than one of them. So with kind of the semantics, it's kind of a best practice kind of recommended to use something like a deny all rule, where in this case, this is a mesh wide config, and this empty spec means we're going to deny everything. And so that means that, rather than kind of the implicit enablement functionality, you're very, being very heavy-handed in saying that nothing is allowed at all ever unless I authorize it. Maybe that's a little too heavy-handed for your organization, but it's something to think about. It kind of makes the mental model a little bit easier. So quickly, let's kind of check in on time. Yeah, we're running kind of low on time. So just really quickly, how this actually is implemented is an other filter in the chain, the RBAC filter from Envoy. And so this is how you actually enforce the policies. This is the actual enforcement point. And so this is the RBAC config. So we're looking at the header and the get. So in this case, the permission is a match on the method pseudo header if it's a get. And so our curl is a basic get. That's correct. We're good to go there. Then the principal is going to look in our dynamic metadata in the Istio authentication filter, check the request auth principal key, and then check the value of it to make sure that it's the correct principal that we defined. And so since in this case it is, that's in the metadata, now we have that's successful. And so the request will be allowed. And so it's kind of a quick journey. Just a quick plug for if you're interested in some of the stuff we're doing at Solo, come check out SoloCon next month. You can sign up here at this address here. But with that, we'll go ahead and stop, and we'll maybe do some Q&A if we have time. But yeah, thank you.